Beh, loro devono sopravvivere in questa situazione, ma hanno altro noi quest'anno dobbiamo comprare
diretta.
C'è anche quello per il filtro per gli AI. Che l'anno scorso non abbiamo trovato. No, per il fatto del prezzi autogestiti che si concentrano che qui c'è arrivato una reference di Doi tutta bella ordinata, però non esiste. Questo è un problema serio. Allora noi teniamo il filtro che per vengono passati sia stato fatto con l'intelligenza artificiale, quindi ti dice la percentuale. È l'unico modo per poter fare. No, guarda, è diventata una giungla di quelle terribili. Una volta vivevamo molto meglio, ora adesso vabbè, vediamo cosa succede. Vabbè, buona sessione. Facciamo una buona sessione. Dai, good session.
Ok. Thank you.
Yes. Okay.
Ah no, è conosciuto. No, sorry. Devi spostare. Maybe it's not necessary.
It's not necessary, I think so. Okay. Okay. Good afternoon for all people, and we start with this section. This section is composed by 5 papers. 3 of them are in presence, and 2 are in coming from I'm sorry, virtual presence. And we have just 20 minutes for paper. I suggest you use 50 minutes for presentation and 5 minutes for discussion at the end. So it would be good if you stop at the end of each paper presentation, and after this we start with a little discussion, some questions that can arise from the public. So if you agree, I start as soon. I invite Daniela Marcangio, coming from Polytechnic Paris, Daniela Marcangio, Vincenzo Totaro, and Alberto Ferruccio Piccini. The paper is titled Certain Effect on the Database in Circulation, a case study. Please, Daniela, you have 15 minutes, the floor is yours.
Thank you.
Okay, good.
Okay, so thank you, Roberto. Thank you all for being here. And the next speech will deal with the study of water circulation and water quality in coastal lagoons. And actually, the focus of the study is to understand how may improve the quality of this kind of particular ecosystems so vulnerable for anthropic activities. The study is a part of an agreement between Arneo Consortium and the Polytechnic University of Bari, where I come from. So, here you can see the agenda. So the next speech, of course, will start with some introduction on the issue. Then I will introduce you the domain under investigation and the methodology we utilize, that is a numerical modeling, some results, and finally we will finish with the conclusions. So coastal lagoons. Coastal lagoons are extraordinary systems, ecosystems. Usually these lagoons are connected to the sea through channels, and it's important that these channels may be, how may I say, they not be stopped, the flux that come inside and outside these lagoons because of the quality of this water. They are rich of biodiversity. They are very important ecosystems. For this reason, is important their quality, and because they are so rich, most of times they are also a area where is very high. Not only the environment, so are important not just for the environmental point of view, but also for the economic point of view. Because here we have several fisheries, aquaculture, so many anthropic activities that make them polluted. And for this reason, it's very important. Here you can see some of these very, very extraordinary, I said again, lagoons. And for this reason, for example, you can see, for example, we come from Italy, so Venice is very famous, but
Just a moment, because the people at top, they don't see the presentation, so we have to share the presentation.
no. You can see entire screen. Yes, this one. Maybe this one. Okay. May you ask to people who did they see?
Yes, okay.
Okay, thank you very much. Okay.
Are you here? Okay. So I was talking about Venice, and you can see, for example, how high can be the pollution of this kind of ecosystems. For this reason, we started to study an area in the South Italy, exactly, it's in the central eastern part of the Salento Peninsula of Italy, facing Mar Piccolo, where we have 6 lagoons, 6 coastal lagoons, connected to several channels to the open sea. And they belong in an area called the marine protected area of Porto Cesario. So they are very rich of biota and several species that make them very extraordinary as ecosystems. And in the past, there were chains of sand dunes that forbidden the mixing of water from the open sea to the inside water, and particularly to come out the water that comes from the rain. And for this reason, this area in the past was stagnation area with the formation of the swamps. So during the years, they constructed several channels to make them open to the sea, and with a regular form of elliptical basin. And among these area, we choose just one of the basins for this tested study, that is Bacino Fede Basin, and is connected to the open sea with 2 channels, one on the left and one on the north, on the right, that is exactly west and east. And you may observe from this figure that it seems to be with water inside the channels, but actually it's not real overall the years, because you can observe, for example, from these pictures, that sometimes the channels are dry, and that this is a big problem. So for this reason, we started to study the circulation and the water quality of this area with a numerical model. Which model? Well, the MIC 21 bidimensional flow hydrodynamic model that is distributed by the Danish Institute, that is well tested in other similar problems of coastal and estuarine estuarine environments. And actually, among the several models it offers, we use just two: the hydrodynamic model for study the water circulation, and the Ecolab model to analyze the water quality. Here on the left, you can observe the most important equation for the hydrodynamic model, while for the water quality study has parameters under observation. We use the BOD and the EOD because we know that when the BOD is low and the OD is high, we can say that the quality of water is good. So for the model, we use just the two forcing functions, that is wind and tides. And we kept the data from a tide gauge station that is in Porto Cesario. We analyzed the years from the data available from 2007 until 2015. And we did a kind of performance, we analyzed the performance of all data. So, as you can observe from the graph on the left, we just choose the years 2011, 2014, and 2015 for the input data of winds and tides. And actually, because they seem to have the highest performance. And actually, we choose just the year 2014 for analyze in each year, which was the most important, let's say, important season where we have the most frequent winds. And actually, it was January, February, and March. So for the several simulations we implemented, we use this data. We analyzed the 3 years and this season. We thought to simulate, first of all, the real case where the two channels have the real depth, that is 30 centimeters. Then we try to understand what happens when the channels can be dry. So it means no water inside, or anyway, less depth instead of the real situation. So we thought of a silting of percentage of 55% and 50%. And in this way, we have 3 kinds of simulation. Also, we wanted to analyze the water quality inside the basin. So we thought of consider two different scenarios. The one where the BOD in both the boundary conditions, that the inlet and the channels, is 0.5 milligrams per liter. That means a good quality of water. While for the second scenarios, we consider 13.36 milligrams per liter of BOD, just for the inlet on the left. Just to to consider a possible pollution from the open sea. What happens in the basin? It's easy for the waters to mix and to dilute this kind of pollution. Here I will show you the results, some results, and let me see if the movie starts. Yes, you can observe. It's very fast, sorry. But what we can see, so it finished at the end, yes, that considering the 3 cases, while the channels are silted, so there is the silting in the channels, we can observe a less elevation in the basins and modest oscillation of the free surface. And you can observe also, you may see okay, it's just over there. Here, actually, this part of the channel is completely dry at the end of the simulation. And I forgot to tell you, we consider this silting for a length of 100 meters from the inlet. The situation for the 2014 year is similar, just we can observe less change, so less depression of the free surface, but it's similar, the same, while we have no dry parts of the channel, so it's better if you want to say. And while the 2015 proved to be the most compromising year, I don't show you the movie, sorry, just to go to the last step, because in this year we can observe the silting of long parts of both canals, as you can observe there. So it's the worst situation. Similar results we obtained with the velocity field. So actually, when we have the silting in the channels, starting from the 15th and the 25% and 50%, we can observe less circulation, less velocity inside the basin. That means less mixing, and so possibly and highest pollution. And the same for this year, just a little bit at the end we observed that maybe here it's difficult, but you have to believe me. The velocity are a little bit higher in this year, but because we had higher tides, so maybe it improved the circulation in the basin. And finally, in this year, we can observe more or less the same conditions among all the different simulations. Here I'll show you just for 1 year to be faster as possible. The results from the Ecolab module. Here, considering the BOD concentration, you can observe that a faster reduction in BOD is observed in the first, you can see the arrow, in the first scenarios compared to scenarios 2. So it means that we need more time that the BOD becomes lower, and so there is again a good circulation inside the basin. While about the silting cases, they react in a similar way overall. About the OD concentration, it's observed that between the configuration without silting, that is scenarios this one, and from the left to the right for both scenarios, the scenarios 1 and 2 means the different conditions at the inlet of the BOD. Okay, while going from left to the right, we can see the different silting, and we can see where the configuration without silting and the one with interruption. Well, in the latter, there is a slight reduction in oxygen accumulation, so it's not good. Anyway, it's easy to believe. So finally, here I have to show you some conclusion about this work. But what is important to see is that with these results, we understood the negative effect of the silting channels for this kind of lagoons. So it's very important if we want to save these very environmentally important ecosystems, it's good to plan maintaining intervention with the stakeholders, with all people in this area, because they need it. So you have observed some pictures in the first part of the presentation. So that's all. I was very careful. Thank you very much.
Thank you, Daniela. Do you have any question, any comment to do about the presentation? Just a question, just to better understand when you speak about intervention and soil maintenance. Could be a good idea to reduce pollution using something that can help to increment the oxygen level inside the water. So it could be useful to use something to mixing the water in the channel, using something that during the dry period, or better during the period in which you have not so much water inside the channel, you can use something that help the circulation using something that help this.
Yes. Yeah.
What do you think about it?
Well, actually, exists several. Do you want? Exist several. Methodology to improve it. But anyway, because they are poor area, just to have a well situation for the channels, it's fine enough. Also because we have pollution inside the water, because there are fisheries and aquaculture.
Yeah.
But it is an agricultural land. So we have also pollution from rains and from land. So if we have a good connection with the sea, as beginning, it's fine enough. Of course, you can oxygen more with with air. There are a lot of methodology, but it's fine to just take out vegetation, sand, because I think it could be enough.
Okay. Okay.
Very simple maintenance.
Okay.
Okay.
Thanks
Thank
a
you
lot.
very much. Thank you.
Thanks, Daniela, again. And go quickly to the next presentation. We have the next, starting now, is a paper coming from Maria Francesca Bruno and Matteo Molfetta and myself. The title is about the influence of the sea level and the water, the wind effect on the beach erosion along the Apulian coast. So please, Maria Francesca, come, and I'll also for you 15 minutes, and after we start with the discussion.
Thank you, Umberto.
Good afternoon to all.
I will present you the influence of sea level and wave storms on beach erosion along the Apulian coastline.
To share the presentation.
It's
Video
a
screen.
session.
Okay. Okay,
Okay.
we can go.
Coastal areas are severely affected by climatic and weather drivers that are weakening the coastal quality. Also, these effects are increasing due to the coastal climate change. The exposure of coastal areas is increasing because there is a growing population along the coastal territories. We have to investigate what is happening to coastal areas because the weather and climatic drivers are reducing the resilience of coastal territories. The low-lying areas in the Mediterranean region is projected to be a hotspot for coastal hazards. So we need to deeply investigate the influence of wave and tides related to the coastal development. We have seen that in the last decade, a widespread coastal erosion has aroused a strong warning in the Mediterranean countries, and mostly in Puglia region, that is located in the southern Italy. And an increasing number of sandy beaches are eroding. To investigate the occurrence of these erosive phenomena, sea level and wave datasets, both modeled and observed, have been investigated in order to to understand the correlation between beach erosion and weather and climatic data sets. So in this presentation, after a short introduction about the Apulian territory, and we will see the shoreline evolution analysis in the short term, in the long and medium term. Then we will see an overview of the examined climatic datasets and climatic analysis. We will see the results coming from modeled dataset from Copernicus and observed data. At the end of this presentation, we will see the results, and we will try to find a correlation between the shoreline evolution and the wave and tidal data. The first step was to define the current situation along the Apulia region coastline. In particular, we used orthophotos acquired in 2017 that was very high resoluted, with a resolution of 20 centimeters. To carry out the evolutionary analysis in the long, medium, and short term, we used the available cartography and the aerial photos starting from 1960 to about 50 years ago. Shorelines have been digitized and overlaid, and the evolutionary trend was assessed through a polygon overlay analysis, so we could evaluate erosion and deposit areas. Now we can see at a very quick classification of shoreline assessed to the evaluation of the orthophotos acquired in 2017, and we have seen that the Apulian coastline has a very complex landscape, because we can find a lot of different situations, starting from sandy beach, very long sandy beach barriers that divide coastal lagoons. We have flat areas with very long sandy beach, pocket beach, and we have also very long rocky and rocky beaches and cliffs. In this slide, you can see three of the results from the polygon overlay analysis. We can see the results for the long term. The comparison between 96 and 1992 shows that the erosion involved 35% of the regional sandy coastline. After World War II, the regional coastline was affected by a growing urbanization that has severely modified the asset of the coastal territory. In the medium period from 1992 to 2005, we have seen a reduction in coastal erosion, and the erosion affected only 18% of the regional sandy coastline. But in the short period from 2005 and 2017, we have seen that the erosion has impacted the 34% of the regional sandy coastline. We have seen that erosion, the coastal erosion, has increased in a very severe way. we can see that in this period, in this last period, we have had higher erosion rates. In some territories, we have seen that the evolution rate was greater than 2 meters per year. In this slide, we can see also the difference for each physiographic unit in the 3 periods that we have examined. And we can see that the eroded shoreline has highly increased in the last period. In order to investigate the last period, we have performed a very detailed analysis. We have exploited also the cartography acquired in 2008, 2010, 2011, 2017, because we wanted to know exactly when the erosion started. And we have seen that from 2005 to 2008, the situation was quite stable. We can see an increase, a great increase, but this great increase is visible in the post-2008 period. In particular, along the Apulian-Ionian side, we can see that the erosion rate passed from 28% to more than 50%. Instead, we can see that the erosional rate increased along the Adriatic side from after 2011. We don't have cartography between 2011 and 2017, but we can see that erosion started after 2011. And we can see that the erosion rate increased, passing from 20% to more than 30%. We have noted that there was a different starting point on the two sides of Apulia region. After 2008 for the Ionian side and post 2011 for the Adriatic side. In order to try to explain this situation, we investigate the climatic data sources, and in particular, we used tidal levels. We used the daily global observation from Copernicus Climate Change Service. We used sea level anomalies that are based on satellite altimetric measurements covering the period from 1993 to 2020. And we used also sea level data recorded by tidal gauge that belongs to the Italian National Tide Gauge Network. And these tidal gauges are positioned along the Apulian coastline. In this map, you can see the point that we used. The analysis of storm events has been carried out using the ERA5 web dataset that is also produced by the Copernicus Climate Change Services. If we see at the results coming from the SLA dataset, we can see that after a Mann-Kendall test, that resulted in the presence of significant increasing trends at all the collected points around the Apulian coastline, we performed a trend analysis to estimate the evolutionary trend of sea level. We have seen that the Adriatic Apulian coastline has experienced notable rising trends ranging from 2 millimeters per year to 3 millimeters per year. But from this map, we can see that in the Ionian Sea, the SLAG datasets suggests that there has been a lower increase in the Ionian Sea, except in the very southernmost part of the Apulian region. This is in contrast with we have found investigating the observed data. We have seen that all the tidal gauge present in the lower middle Adriatic highlighted a generalized increase in mean sea level starting from 2008 with a variation between 27 and 29 exceeding 10 centimeters, with a maximum recorded at the northern part of the region and a minimum in the southern part of the region, ranging from 10 centimeters to 13 centimeters. We have seen that after a sudden increase in 2011, the mean sea level has again risen, reaching a maximum values in 2012 and the southern Adriatic station. If we look at tidal data recorded in the Ionian Sea, we can see that the trend is similar to what we have seen in the Adriatic side. And this is in contrast with the results from Copernicus. We have seen that the mean sea level recorded in the Ionian Sea has risen by approximately 13 centimeters in the period 2008 to 2007 to 2009. We can see that all the tidal gauge present the same behavior. If we look at the wave data analysis, we can say that the effect of the sea storms on the coast depends on various factors, such as the wave height at the peak of the storm, their direction, wave periods, and also the direction of incidence. Moreover, it is important that it's important to highlight that in case of closer storm events, the effects of the coastline can be more destructive. For each storm, we have estimated the total energy as the product of the period, the energy mean period, and the wave heights. And we have selected the storm events from the entire wave time series following the storm definition proposed by Bocotti. And for each storm, we have estimated the total wave energy flux that has been obtained by applying a time integration along every single event. Then we have classified storm events using a Fisher-Jenks optimization algorithm for splitting the storm dataset into 5 classes based on total wave energy, spanning from weaker +1 to extreme +4. If we look at the total wave energy, we can see that the analysis of the total wave energy recorded during a very long period, about 70 years, has revealed significant variability over time across all the examined points, both in Adriatic and Ionian Sea. But we can see that the Ionian Sea appears to have a higher wave energy if compared to the Adriatic Sea, except for the points located near the coast in the Gulf of Taranto. We can see from these graphs that the Ionian Sea has a low wave energy in the period 2005-2007, but in the winter 2008-2009 we had the winter maximum wave energy in all the 70 years. If we look at the bottom panel, we can see that in the Adriatic Sea, in the period 2005-2007, we had also a low wave energy, but the higher wave energy started in the period 2011-2012. It's a very different behavior along the two coastlines, Adriatic and Ionian coastline. If we see the storm classification, we can see that in the Ionian Sea, that is the upper panel, in years 2008, 2011, 2014, the total wave energy flux exceeded the value estimated as the mean plus the standard deviation. We can see also that in the bottom panel in the Adriatic Sea, the total wave energy exceeded the threshold value in 2011, 2018, and from 2011 to 2014, the total wave energy exceeded the mean value in most of the years. We can see also from this result that the Ionian and the Adriatic Sea had a very different wave energy in those different years, from 2008 for the Ionian side and from 2011 for the Adriatic side. If we have a closer look at these storms, in particular, we have estimated the storm characteristics such as the number of storms, their duration, and the time delay between storms in order to understand if clusters of storms had occurred in those periods. We can see that in the Ionian Sea, in the period post-2008 from to 2011, the number of storm events consistently increased with very short intervals between them. In 2008, there were 10 storm events with an average interval of 12 days between each occurrence and a very long duration with an average value of about 100 hours. If we see at what happened in the Adriatic Sea, we can see that 2011 was the worst year concerning the combination of the number of storm surges, their intervals, and duration. Also, if we look at the characteristics of the storm, we can see that the difference between the two sides, the Adriatic and the Ionian sides, were big. Now we can conclude that in the recent period, erosion has affected more than the 30% of the regional sandy beach, with a large increase respect to the previous periods. For the Ionian Sea, the highest erosion rates began after 2008, and the mean sea level has risen by approximately 30 centimeters in the period 2007-2009, and cluster of exceptional storm events occurred from the winter of 2008. For the Adriatic Sea, we have seen that the coastal erosion has significantly worsened after 2011, and the mean sea level rapidly increased starting from 2008, with a variation between 2007 and 2009 exceeding 10 centimeters, ranging from 13 centimeters to 10 centimeters. After a sudden decrease in 2011, the mean sea level has again risen, reaching the maximum value in 2012. And we have seen also that the most severe sea storms occurred in the period 2011-2014. This combination of high mean sea levels and sea storms that were characterized by high energy content and a short interval between them has certainly contributed to enhance the observed erosion phenomenon. This is not the only cause of the beach erosion, but this combination of mean sea level, of increased mean sea level and higher wave energy has surely contributed to this situation. Thank you.
Thank you, Maria Francesca. Do you have any question? Some question to arise about this paper? Okay, no question at all. Thanks you, Maria Francesca. We start with the next one. Next one coming in virtual presence is a paper coming from Carlo Barletta, Alessandra Capolupo, and Ofema Tarantino. The title is Estimating Urban Growth from Landsat 8 Data Using Post-Classification Albedo Change Analysis in OEE Environment. I think that the speaker is Carlo Barletta, right?
Yes.
So, okay, the floor is yours. Carlo, you have 50 minutes to start, starting from now.
Okay, thank you. Hi, everyone. I'm Carlo Barletta from Tecnico di Bari.
A few minutes just to start with the presentation. Okay, okay, thanks a lot.
Okay. And I'm going to present the results of our work.
Can you share your screen, Carlo, please? You have to share your screen.
It's not shared.
You have to close
Okay.
your window.
You have to close the down.
We are still
Yeah.
sharing ours.
Do you see the screen?
Yes,
Not
yes, it
the-
works.
The Roberta screen?
No, it works.
It's not.
Go out. We'll help you. That should be more.
Okay, but we can see the screen from home.
Yeah, but we
We don't see nothing now. We
Oh,
send
okay.
just a screen you will see.
Okay. So do you want to? It's Scarno, this one. Where do you share? share. Okay.
Okay. Good.
Okay. Try you to share your window. Or if not, we will share this one.
Okay, I'm okay. Schermo.
Doesn't work, we will share our.
Okay.
Now,
No.
No,
Yeah.
so let me share. Let me share our window.
because I'm sharing the entire screen.
Okay.
Entire screen. That
Okay.
one. That one. That one. Good.
Okay. Let's see. Stop sharing. Okay.
No.
No. If you want to do it.
Share.
Try and stop sharing. Okay. Try screen. Yes. And try this one because before we tried this one. Okay.
No.
No. No, this is the registration.
Comes from here.
If it doesn't work, we can ask him to give us the presentation and we will go through.
Okay. Okay. Could be an idea.
Yeah.
Okay.
May you share in the chat your
Your presentation in the chat.
send
Okay.
us your
Okay.
presentation. And you can
We
say go
try to-
on and we go.
Okay.
Maybe it's heavy, I don't know.
No. Okay.
Can we ask somebody how to fix
How
it?
to? No.
Try something.
Ma fin qua ce ne abbiamo tante, sì,
Non
chiudi
so,
tu,
chiudiamo.
scegli, stop sharing.
I can share
I go to see the
chat
presentation.
or
Oh, wait.
okay.
Cioè, no, you have to, you can close. Okay. This one. Two and two.
Okay,
All right. Thanks.
Okay.
Okay, Carlo, you can start.
Okay, I was saying I'm going to present the results of our work entitled Estimating Urban Growth from Landsat 8 Data using Post-Classification and Albedo Change Analysis in Google Earth Engine Environment. The urbanization process is now considered one of the main drivers of land cover change worldwide. The urban growth, which is the increase in artificial surfaces resulting from the construction of new buildings, roads, or other paved surfaces in urban areas, leads to the soil sealing phenomenon, which is today considered a kind of land degradation and a serious environmental issue. Sealed soils, in fact, can negatively impact on the ecological functions of the soil and affect several issues, including the urban runoff, the heat island effect, water and soil pollution, and biodiversity loss. A proper monitoring of land cover changes and urban growth provide valuable information for a sustainable land management. Earth observation data and remote sensing techniques are very adapted to acquire continuous information on the land surface at various scales of analysis. Moreover, land cover changes can be detected measuring from multi-date satellite images the variation in biophysical variables such as the land surface albedo, which is the proportion of solar radiation reflected from the Earth's surface. Landsat mission appears very useful to address such issues since it's the only source of free images acquired in more than 50 years with a resolution adapted for urban analysis. The objective of this research was to develop an innovative hierarchical model which integrates a novel index-based classification method and albedo change analysis in order to extract information on land consumption occurred on urban areas using Landsat 8 satellite images. The change detection approach, which includes both the post-classification and the image differencing methods, was applied on the study site of Bitrito in southern Italy, in Apulia region, for the period 2015 to 2023, using the Google Earth Engine cloud platform. In this slide, we see the workflow which was followed in this study to achieve the aim of the research, and on the right, the Earth observation data used. Initially, cloud-free satellite data acquired in summer period for the years 2015 to 2023 were used for the land cover classification. Then Google Earth high-resolution images were used for the accuracy assessment of the classified maps. And these maps then underwent a pixel-by-pixel post-classification comparison. Then for pixel classified as changes, an image differencing step between two albedo maps obtained from late winter satellite images was performed, and last was performed to remove false changed pixels and to refine therefore the change detection. Lastly, a pixel to filter to remove isolated pixels, so to remove noise in the final image, was also applied to obtain the final change map. Now we can see more specifically some of these phases. In particular, here we see the novel index-based classification method, which was developed for this in this study. This method involves a decision tree hierarchical approach, which allows to extract sequentially 4 land cover classes: vegetation, plastic greenhouses, urban areas, which includes all the artificial surfaces, so all the built-up building construction, but also roads or other paved areas, and lastly, the bare soil. This method allows to extract, as said, sequentially these land cover classes by defining appropriate thresholds of STRED and SWIRED indexes, but also near infrared to shortwave infrared ratio band and near band of Landsat data. Now we see briefly the training stage. Several training pixels were chosen over the study area of Vitritto, and these training pixels allowed to extract the spectral signature plots and some scatter diagrams. In this method, first the vegetation is extracted by defining appropriate thresholds of STRED, SWIRED, and near band. Then the plastic greenhouse are extracted by setting thresholds of near to SWIR to band and near band. And lastly, threshold of the SWIRED index are used to discriminate the urban surfaces from the bare soil. Now we see the algorithm which was chosen for the estimation of the land surface albedo maps, and it was the Da Silva algorithm, which was developed in 2016 specifically for Landsat data. As said previously, the change detection method consisted in an integrated approach involving the post-classification comparison and the image differencing methods. After applying the post-classification comparison pixel by pixel for the resulting changed pixels, in particular those from non-urban to urban, here called soil loss, a suitable threshold of albedo change, which is possibly representative of a significant land cover change from non-urban to urban, was found. More specifically, an increase in albedo higher than the threshold in late winter images. And late winter images was preferred because in this period it is better to discriminate the bare soil from the urban surfaces, since the higher moisture content and the green cover cause lower albedo values for the soil compared to the albedo of the urban areas. So an increase in albedo higher than the threshold allowed to confirm that the pixels identified and marked after the first phase, after the post-classification comparison, belong effectively to the class which now is called urban growth. Therefore, the final change map consisted in two main categories, urban growth and no growth. And now we can see better the land cover maps which were obtained with this index-based method. We see the classified maps for the years 2015 and 2023 for the study area of Vitritto, with four classes, which were vegetation, urban areas, bare soil, and plastic greenhouses. From the accuracy metrics, we can observe that the overall accuracy was high for both maps, and in particular, the extraction of the urban areas class was very good, with accuracies higher than 85%. These maps were then aggregated into a binary classification scheme, including only two classes, non-urban areas and urban areas, where non-urban areas is the result of the aggregation of vegetation, bare soil, and plastic greenhouses. These two maps for the years 2015 and 2023 underwent the post-classification comparison, which was described previously. In this slide, instead, we see the land surface albedo maps, which were obtained through the application of the Da Silva algorithm for the study area of Vitritto. These maps underwent were subtracted for the image differencing method, which was mentioned previously. Now we see finally the final urban change map, which shows the areas which changed from 2015 to 2023. So this map has two categories, urban growth and no growth. we can see that from the accuracy metrics that the overall accuracy was found to be very high, totaling 92%. And for the urban growth category, satisfactory results were found with a producer accuracy of 85% and a user accuracy of 77%. So the land consumption for Bitritto for the years 2015 to 2023 was found to be moderate. Furthermore, the high values of the accuracy metrics suggest that this method could be reasonably applied in the future to contribute, thanks to its relative simplicity, to the rapid monitoring of urban development and so the land consumption also in other areas of the Apulia region. In conclusion, this work allowed to extract information on land consumption for the area of Bitritto in southern Italy for the years 2015 to 2023, where a moderate land take occurred during the period considered. A combined approach between a post-classification comparison among two land cover maps obtained through a new index-based decision tree approach and the image differencing between late winter albedo maps obtained from Landsat data provided the satisfactory results in terms of the accuracy of the final urban change map. Lastly, the Google Earth Engine platform, which was used in this study to minimize the acquisition and operational time thanks to the cloud technology, was confirmed to be optimal for analyzing and monitoring over time the evolution of land surface features. Thank you for your kind attention.
Thank you, Carlo. Is there any question to this presentation? Okay. Ask something to the
Yeah.
Yeah.
Can I ask something? I would like to ask Carlo if he applied LICAI algorithm which was proposed by the Agilab laboratory. In which is the innovation in this paper?
Yes, the innovation in this paper compared to the LICA algorithm was that derives from the extraction of the vegetation, because in the LICA algorithm the vegetation is extracted only with the STRED index. In this case, the use of SWIRED and the NIR indexes allowed to better discriminate the vegetation, in particular to avoid that roads were misclassified as vegetation. Another innovation is that the extraction of plastic greenhouses, which allows to better to avoid that this kind of land cover goes in the urban areas. And lastly, the threshold of SWIRED, the SWIRED, which were the SWIRED was already adopted in LICA for the extraction of urban areas, but after these two steps, the extraction of urban areas resulted to be slightly more accurate in this case.
Thank you.
Okay. Thanks, Carlo, and go quickly to the next presentation by Alessandra Capolupo, Pietro Marco Santoro, and Eufemia Tarantino. The title of presentation is capturing. Okay, capturing sentinel data in Google Earth Engine for partner area classification, expense classification by I think that, okay, Alexandra, the floor is yours. You can start with that. You have 15 minutes to start.
Okay, thank you very much for the floor and good afternoon, everyone. I'm trying to share the video, so please let me know if you see it.
Okay, you have to share the presentation.
Yes, just
Your
a
screen, please.
moment, because in this moment it's blocked.
Okay.
So
Perfect.
wait, maybe I can try again. I can try to. Okay. So.
Thank you.
Perfect. So, good afternoon. I'm Alessandra Capolupo, assistant professor at the Politecnico di Bari. And now I'm going to report the preliminary results of one research that we are conducting at the AlgiLab laboratory. And in particular, in this research, we are going to show you the results obtained by Pietro Marco Santoro in his bachelor thesis. So what we did, actually, we just analyzed the potential of the medium resolution Sentinel-2 data in order to estimate and quantify the burned areas by developing a proper JavaScript code in a Google Earth Engine environment. Why we decide to analyze the wildfire? Just because actually we know that in particular in the summer period, the fire can be recognized as one of the main natural disaster, since it destroyed everything it met during its path. However, contradicting any kind of convention, the fire is not always negative, because sometimes it can be adopted to regenerate the soils, because thanks to the controlled burning processes, we can release nutrients into the soils, and so to help the plants to grow healthily, as well as also we can avoid the diffusion, the spread of the invasive species in contrast to the native species of specific areas. So, however, in the most of the cases, we are not treating with the controlled burn process, but we should face the damage caused by the wildfires. Because we know that this kind of process could cause a loss of biodiversity in our ecosystem, and also by destroying the built-up areas, so the built-up environment, it can cause also a lot of social and economical damages to the people that live close to it. So for that reason, it's really important to detect the most proper planning strategies that can help the policymakers to detect this natural disaster in real time, and also to quantify their damages in a really short time. For sure, the geospatial big data play a crucial role in this process, because according to the scale that we want to, according to the scale of our analysis, we can choose the proper sensors mounted on a proper platforms. For sure, if we want to analyze and we want to investigate the damages on a large scale, we should use the satellite images. And however, also these techniques is not limitation free, because because the selection of the proper platform is affected by satellite temporal and spatial resolution in particular. So among the various open source platforms that are available in this moment, for sure, the Sentinel-2 is one of the most common use for this purpose, because since it is characterized by a twins of satellites, it has a temporal resolution equal to 10 days. So this could be really a good option, because it allows to detect viable images really close to the event that we want to analyze, because usually we should select one image before the event and another one after the event, but most of them should be really close to the event. Actually, the Sentinel-2 data are not the only product that is provided by Copernicus that could be useful to meet the purpose of this research, because if we analyze its dataset, we can see that they provide also the European Forest Fire Information System that is characterized by the database that is that involve all the events that were registered across Europe along different times. The EFIS data were obtained by the MODIS satellite platform. So it means actually that the resolution was not really satisfactory because it's around 250 meters. And so before the 2019, this dataset was useful just to identify the fire that covers an area that larger than 40 hectares. But if we want to analyze the last events that were carried out in the last few years, it was able also to analyze the areas that covers an area with the size of 5 hectares, more or less. So for sure, the accuracy of this data was improved over the years. The most difficult things in this case is just that we should analyze a large volume of data, and so not all the platform that the software that we should apply to handle the spatial data are satisfactory. In this case, in order to go beyond this issue, we decided to apply the Google Earth Engine environment, that is a cloud-based platform released by Google in 2017. And this really aimed at storage and handle the geospatial big data. So what's the aim of these research activities? We want to estimate the damage occurred after 2 small wildfire events occurred in Vico del Gargano in Bitonto, in Puglia region, in the southern of Italy, by taking advantages of the medium resolution Sentinel-2 data and the EFIS data. So in order to achieve this purpose, we apply an index-based classification method, because it is the characteristic to help the user to quickly classify really large areas. So it could help us to speed up the procedure. And all this process was implemented in Google Earth Engine by developing a proper JavaScript code in such environment. So here is reported the operative workflow that we applied in this research. And if we look at it, we can see that it could break down in 5 main steps. Indeed, first of all, we create the geodatabase that involves both the Sentinel-2 data that were selected and collected to analyze the fire events in Bitonto and Vico del Guardano, as well as the EFIS data. To be honest, in this case, we decided to select 4 images for each case studies and not 2 of them. So we collected the 2 images before the event and the other 2 after the event per each case studies, in order to reduce the issues, the potential error introduced by clouds and shadows, and their shadows. After that, we started also with the pre-processing steps. And so all the 4 images are actually the 8 images if we consider both test sites were atmospherically and radiometrically corrected. And just after that, we introduced the index-based methods. Amongst the various algorithms that we could adopt it, we decided to apply the normalized Barn ratio index, since from literature we know that it is one of the most common used because of its performance. But this gives us just the possibility to create the thematic maps of our study areas, but it is not really able to estimate the damage that was occurred. And for that reason, we arrived at the first step of our process. We apply the bitemporal change analysis. Indeed, when we want to analyze the changes occurred in a specific area, we could choose if apply the bitemporal change analysis method or the track changes approaches. Among them, we decided to we preferred the former. We preferred the former just because in order to speed up the procedure, and also because usually the output that is produced by applying these kinds of approach is more accurate than the other ones. To apply the bitemporal change analysis, two different indices were applied: the delta normalized Barr ratio index and the revitalized Barr ratio index. Both indices are used usually to quantify the damages occurred after a fire event, but the former is more used in an area covered by dense vegetation. Instead, the second one is more suitable for extracting such information in the areas covered by discontinuous vegetation, and so it could also adopted in urban areas. In both cases, in order to follow the recommendation of the European Fire Forest Protocol, we classify all the areas using 7 different classes, from the enhanced regrowth to the high severity, and for each class was used a different color. So after that, finally, we analyzed the accuracy of the thematic map that we obtained, and to do this, we computate the overall accuracy and the couple coefficients by using the sample that were extracted from our raw Sentinel-2 images that were applied to obtain such thematic maps, and that samples were extracted by photo interpreting their satellite images. And in addition, we also use the samples that were extracted by the EFIS data in order to see how the accuracy of our thematic map varies according to the reference data set that we were using. So what we can see that we obtained 2 different thematic maps for each case studies, and in particular here you can see the difference between the delta normalized Barr ratio index and the revitalized Barr ratio index, and also we quantify the pixel and the area covered by each class for each thematic maps that we generated. So if we analyze these results, we can see that in both cases, the trends of the 2 thematic maps are similar, even if the revitalized Barr ratio index underestimates a little bit the values of the different pixels, so underestimate the damages that we can analyze. And this trend is perfectly comparable also with the results, the funding that were obtained for Bitondo, and also they are similar to that one that were previously obtained by other research activities. So maybe this result is mainly due to the fact that the 2 indexes are completely different, because they should be adopted in 2 different case studies. However, to be honest, both of them shows a really high correlation with the field measurements of the damage caused by the fires. So in order to also evaluate the performance, we analyze the accuracy of the resulting thematic maps, and by comparing the results we can see that for both case studies, the overall accuracy and the kappa coefficients were higher when we compare the accuracy using the sample extracted from the same data set that we use for obtaining the same, for obtaining our thematic map. So this result means that it is mainly due to the resolution of the data set, because we said before that the FEC data is less accurate than the data sets that we can use for photo interpreting, because the resolution of the raw data that were used to extract them is lower. So what we can say in conclusion, for sure, we assume that the Google Earth Engine platform could be considered as an optimal tool for implementing customized scripts that could meet the user needs. And so in this way, so we can create a code that is scalable and adaptable to the size of the areas, to the scale that of our analysis, but also to the geographical areas where we want to perform this analysis, because actually this code here could be easily modified to change the input data as well, also the scale of the analysis. At the same time, we can also say that the Sentinel-2 data has a resolution that is enough to analyze the damages that were reported at small wildfires, and also actually they were also useful for meeting a monitoring purpose. And lastly, regarding to the consistency and the robustness of the two indices that we apply to quantify the damages reported by our method, we can say that both indices shows promising results that are perfectly aligned with the literature, and also that the trend is comparable, is completely comparable. So it means actually that their performance is completely independent from the geographical areas where we are working on, and they are really useful to meet the purpose of these studies. However, usually the revitalized burn ratio index shows more accurate result than the delta normalized burn ratio index. So thank you for your attention.
Thank you, Alessandra. Thanks a lot, Alessandra, for your presentation. Is there any question about this paper, this presentation? If all is clear? I hope so. You think so? Okay, thanks, Alessandra. Just a question. What is the next about this topic?
Okay.
So you have to suggest something in the next future about in order to enhance the robustness of this index and try to find in a different location with different vegetation or something like this, in order to have a better idea about application, universal application of this index?
Yes, actually, in the future, we don't want just to apply these indices in a different geographical location, but we want to improve our algorithm, that's the algorithm that we adopt. So for that reason, actually, we should pass from the index-based method to the machine learning algorithm. Indeed, we are just applying some different algorithm that should improve the accuracy of our final findings.
Okay, I got it. Thank you very much, Alessandra, for your presentation. We are arriving at the last one, and the next one is coming from Jacobellis and Gloria, Totaro, and Leonardo, and many others. Okay, and the topic is related to estimating about water management in southern Italy through hydrological model and Google and satellite data. So Vito, please.
Yeah, thank you. Do I need to share the screen?
Okay, perfect. Thank you very much. Okay. So, yes, many others, as you can see, because this is quite a large group, because it is compounded by all participants of a project funded by the ICCSA, Italian Space Agency, and it involves a number of partners. Let's see if I manage to go next.
Not good better to use. Because it's not connected, it's better to use.
Which one?
Task.
Okay. Yes, and so as you can see here in this slide, there is the number of participants of this project, whose name is TETIS. It stands for Earth Observation for the Early Forecast of Irrigation Needs. Actually, the project comprises contribution from Polytechnic of Bari and National Council of Research, IREA site, the informatic group of the University of Bari, and the CREA, which is who's working on agricultural needs, and last but not least, the consortium for agriculture, which is the main stakeholder. And here on the right of this slide, you can see the main part, sample of the architecture of this project, which is basically what we need in this presentation. The main object of the project is to make early forecast of irrigation need. It is composed by a hydrological model, water balance, here, which provides input to a crop growth model, and to provide, of course, irrigation needs. The remote sensing area is provided by information about surface soil moisture and the beta index, basically. It exploits Sentinel-1 and Sentinel-2 data. It also exploits SAOCOM data from Argentina. The part of these images are used to the early detection of the irrigation area, because one problem is actually to detect how much area will be irrigated and will be actually planted with tomatoes. We focus mostly on tomatoes in this project, but also surface soil moisture. And about this topic, I will focus mainly this presentation. Here is also an important part of the project, because we have satellite surface soil moisture, which provides input to one of the two hydrological models that we exploit. The first one is SMAR, which stands for soil moisture in the root zone, and the DREAM model, which is a more classical distributed conceptual water balance model. And so the line is that we use, I don't see anymore, we use this surface moisture data to provide input to the SMART model. The SMART model produces the soil moisture in the root zone, and this information is passed to the DREAM model, and the DREAM model provides information to crop growth model. Basically, it is mainly an issue of initial condition of soil moisture at the moment in which this early forecast begins. We have 3 steps in early forecast. We have 2 steps in early forecast because we have a first one in the end of March, which is before plants are seeded. A second one at the end of May, when the starts the main irrigation needs, and the third one in June, where the season is more developed. This is a quick, don't say quick. We were in another window, one of the presentation.
I think you
They are working
This one is okay.
Okay, they are one what?
This is, I will go maybe, Umberto, if you give me the time, because
Yes,
I don't want to
yes,
run through
I
it.
gave, you have 5 minutes, 7.
Okay, thank you. So this is a resume of the DREAM model, which is a quite complete model, and it provides all the processes of vertical and sub-horizontal water balance at the basin scale. So it runs all over a 2,000 square kilometer basin. And it is a particular feature, which is the redistribution of the soil water content, which is provided by a weighted index based on the topographic index of Belen and Kirby. While this is a quick resume of the SMART model, which is actually the focus of this presentation, because those are our first results in the project itself. And so it provides soil moisture S2 in the root zone layer, starting from observation of surface soil moisture in S1. It is basically a stochastic function which has 4 physical parameters, and it is physically based. And the 4 parameters are object, they need calibration. This model has been already exploited in several other cases. This slide you can see in green, the first application of the model without changes. Then we have a number of changes because this model is more suited for arid or semi-arid areas, like the one of our pilot area, but it needs some more refinements in humid areas, maybe also more parameters. It has been used also with a Kalman filter equation for the use, the integration of different kind of remote sensing data, because of course it can use both with in situ ground observation or remote sensing data, different kind, different scale. So I will go maybe faster about the different strategies that have been used in the past and relative concerns. I will better focus on what the use we have done so far in this project, because this project is aimed to monitor ground data, but still these data are not available. They will be used later for checking. So our first application has been one of those that has been already provided in literature, and it comes from the combined use of the SMART and DREAM model, where the run of the DREAM model is used actually to calibrate and to verify the output of the SMART. And to this, obviously, there are a number of problems of scales, because the DREAM model can work to a resolution of 100 by 100 meters, and it works all over the entire basin, Candelaro Basin, while the SMART is basically a vertical model. So we have 4 points where we can check the two models each other. And actually in this phase, we calibrated the SMART model all over these 4 points by using SMAP L4 data, which is obviously a well-known product, quite easy also to obtain and to use. We used we made a daily average of the 3-hourly surface moisture with a resolution of about 9 kilometers of grid. So when we go to look at the overlap between our study area and this map data, this is the pattern that you can see. Of course, these sources are SMAP data. This is the entire Candelaro Basin. These are 4 points. We have one here where there is natural vegetation, and 3 points inside the irrigation district, which is this red line. And the first results, anyway, are quite encouraging, because in this picture we can see the red dots, which is just SMAP data. So it is surface soil moisture all over the calibration and validation period. And the blue line is the soil water content provided by the DREAM model, which receives an input, basically rainfall, ground measured rainfall, and ground measured temperature and other hints and other variables that we need to evaluate evapotranspiration. And the green line is the SMART value, is the soil content in the root zone evaluated by this smart model. And the results are quite encouraging because it's not easy to find such a good agreement between soil surface data and root zone data. There is a nice pattern, and there is also quite a good confidence about the value of the soil moisture that we had to evaluate at the end of March, which means more or less here, in the moment where it starts the prediction, which is then provided by Apacrop, coupled with the Copernicus prediction of meteorological data. And also, we have quite good agreement, also at the stage of May and at the stage of June, which are the other 2 points of our early prediction. We have, as you can see, some, let's say, detachments later, which can be just, could be just model error, because the error is quite small. But it could be also irrigation, because irrigation is provided by SMAP, but it's not used as input in the hydrologic model, because in the hydrologic model we only introduce rainfall. Okay. And we have similar results all over the 4 points included. It is the number 1, which is the site 1. Site 1, which is the one with natural vegetation. And so we see in all other, we see maybe a slightly better fit in summer in the natural vegetation site. And we see some more difference in irrigated areas. Maybe it's just our hope, but at least it is a small model error. Also, this is a check about the parameter values of the SMART model, which were obtained actually based on this calibration experiment that are in line with the literature values. So I think I can go to the end. This is just the starting part of this project. So we have a number of other steps to develop. In particular, it is very important the detection of irrigated areas with areas tilled in as soon as they are tilled, and the areas inside the district where tomatoes are actually planted. Because in that irrigation district, of course, it's not all tomato, but the area with tomato is just, let's say, a good 20%. Okay, that's it. Thank you.
Okay, thanks a lot, Vito. Is there any question about this last presentation? Some to ask the speaker? I think it seems no. We are close to the end. I say people outside for the coffee break. So you are. Thank you for your presence, your attendance, and I hope to see you next day. And have a good afternoon. Have a good coffee break. Thank you a lot. Have a good day.
Cosa devo fare?
No, se vuoi là.
Io.
Aspetta qua.
Cosa devo fare? Devo fare
No, niente, no,
se
vuoi là.
Grazie.
Che si arriva a questo. Yeah.
Devi prendere la maglietta. Se questo è capace di questa performance.
Sì, infatti una volta.
Così come ho dormito.
Anche noi.
Così come non ho dormito.
Anche noi.
Senza valigie.
Senza valigie.
Lo so.
Sì, tutti e qua.
No, io sto caricando la valigia, tu stai caricando la valigia?
Sì. Sì.
Hello. Does anybody hear me?
Good evening, everyone. I think we're going to start the first presentation. We have her here, and the other one are virtual. I don't know how many of you are present. Sarah and Edward, any of you are present here? No. Najada? No. Maxim?
Yes, I'm here.
Okay, and the next one, sorry for my pronunciation, the group of Maxim.
Dmitry, he is also here.
Okay, perfect. So, we missed two lecturers, so we can start. Okay, I will leave the floor to you. The first presentation will be, is there any space in land? That one, right?
Yes.
Yeah. Is there a space in landslides, sustainability modeling, a case study of Valtellina Valley, northern Italy? So I leave the floor to you if you want to share your presentation with the other. Okay. You have to share yours.
Yeah.
Yeah. Yeah, because YouTube.
Oh, yeah, it's
Okay.
okay.
Perfect. Thank you.
Did you? I think. Yeah, we will share again. It's disconnected just now. Just keep it up on that. Thank you. Yeah. Is it? No. Is it? Stay. Give it a moment. Once it's happy, okay.
Yeah, 15 minutes.
All right. Good afternoon, everyone. My name is Ken, and with my co-author Victoria, we are from School of Community and Information Systems, Singapore Management University. And today we are going to present about our paper called "Is There a Space in Landslide Susceptibility Modeling?" with a case study of Valtellina Valley in northern Italy. Okay, so before we start the presentations, we would like to give a short brief on our research motivations. So landslides refer to the geomorphic phenomena of slope failure and mass movement. And based on a recent study, the frequency of landslide events has increased by tenfold over the past 5 decades. And although they have lower casualty than other disasters like typhoons and tsunami, landslides have huge impact on urban development of the neighboring settlements. And moreover, traditionally used engineering prevention mechanisms such as terracing and concrete surfacings to mitigate landslide risks. However, these approaches are costly and challenging to implement as well due to their wide scale that needs to be considered. And in this sense, landslide susceptibility modeling can help as a decision support tool for planners and engineers by identifying highest risk area within a study region. And from that information, the planners and engineers can prioritize areas that require immediate intervention efforts. Moving over to landslide susceptibility modeling, many art geoscientists as well as computer scientists have explored different models ranging from mechanical models to statistical models and even machine learning models recently. However, although there has been a lot of models that have been explored in the literature today, some of these models show exceptionally high performance, and however, there is not much explicit attention that has been devoted to the fundamental properties of spatial data. And this is exactly the motivation behind our study. As a result, our study focused on the concept of spatial non-stationarity, which is a condition where a simple global model cannot accurately represent the relationships between the variable sets and the target outcomes. This is due to the variations in the local spatial structure of the data set. And if we cite the Tobler-Fest law of geography that everything is related to everything else, that near things are more related than the distant things. That is, nearby observations within the same data set shows relative similarity than the distant one. This is a spatial phenomenon called spatial dependence. However, when we use global generalized models that has been explored widely nowadays, this model assumes constant relationships between the set of variables and the outcome across the space. And as a result, spatial data sets, when we use spatial data sets for spatial analysis, these global models violate this assumption. And that is the reason why it is a critical research area for computer scientists, particularly to identify how we can calibrate models to incorporate spatial structures to address the spatial non-stationarity issues that we just explained earlier and produce more ground-realistic inference. So this is the research design overview of our study. We set a total of 4 research questions as listed here. First, we seek to identify landform properties and human environmental factors that affect landslide susceptibility. Following that, we assess whether their contribution to landslide has constant or variations over the space. Next, we also question whether landslide susceptibility is geospatially independent. And finally, we investigate whether local models perform better than global models for landslide susceptibility. And in terms of modeling techniques, we decided to focus on statistical models and explore how global and local statistical models work to model landslide susceptibilities. In particular, we are looking at logistic regressions, which is where established statistical technique for binary classifications, and its spatial variant called GWLR, which is geographically weighted logistic regression, which is a local regression framework introduced by Fotheringham, Shurton, and Grisens. Details on the model formulation of GWLR will be explored in the subsequent section as well. Next, this is a brief about our study area, Valentina Valley, which is located in the Central Alps of the northern Italy. And the reason that we decided to choose this area as a study region is due to its characteristic geomorphology, as well as the recent surge in economic activities and human settlements within this area due to the wide agriculture and ski tourism. So we would like to see how human environment interaction factors can affect landslide susceptibilities particularly. And this is a methodology approach of this study. We started with the data collections of landslide inventory, then the data preprocessing of the landslide variables, which is followed by feature selections to shortlist variables for model training of global logistic regression and geographically weighted logistic regression model. And after model training, we carry out model evaluations to compare the model performance. And finally, we produce a landslide susceptibility map as well as landslide factor coefficient maps. Next, my co-author Victoria will walk through the step-by-step process of our methodology approach as well as the results and finding of our studies.
Thank you.
Yeah, so let me go through with you our data preparations. We took a few steps to do it. So first, we tried to finalize all the layers from our variables into rasters. Then we conducted random strategic point sampling for our landslide samples from our landslide masses, as you can see. And we also performed random stratified point sampling to gather our non-landslide samples. So once all of these were done, we could calculate and derive the zonal statistics for each variable. And for categorical variables like lithology, underwent further encoding such that they were assigned a binary value. So for instance, if there's an absence of metamorphic lithology, that will be encoded to 0, whereas the presence of it will be encoded to the value of 1. Furthermore, within the R environment that we adopted, so we coded in R, we conducted feature selection to ensure that our variables observe low to moderate multicollinearity, and we also further verified the severity of our multicollinearity between the variables using a variance inflation test. So according to our literature review, a variance inflation factor of less than 5 is considered acceptable. And with that in mind, we tried to filter for all the variables that met this criterion so that we could also try and reduce the dimension of our model. And we did so with stepwise selection, which resulted in us getting a selection of 8 variables. And these 8 variables that were selected range from slope angle, land use vegetation, profile curvature, plan curvature, plutonic lithology, and metamorphic lithology, average precipitation, and also proximity to load. Like what my co-author Kant shared earlier, since many models fail to consider the concept of spatial non-stationarity, we explored the use of geographically weighted logistic regression, GWLR. And GWLR is unique from other models due to its weighting function. So what this weighting function does is it determines a spatial weight according to the distance between observation points. So this means that from a given observation point, the nearest observation to it bears the greatest spatial weight. And furthermore, in the weighting function, there is also a bandwidth to specify the distance from each sample point over which the weighting function is applied. By extension, there's also an adaptive bandwidth that adapts to the most optimal size that it can get in consideration of the density of the data points. So after conducting our model training with the global logistic regression model and our local GWLR model, here's a summary. So the sample size we got was we used is about 2,800 data points, and there's about 1,200 landslide points and almost 1,600 non-landslide points. And the kernel function in the GWLR model can be calibrated according to different distributions, but for standardization, we decided to adopt the Gaussian distribution. We also calibrated the GWLR model to the adaptive weighting function, and we used the bandwidth of 76 nearest neighbors since it gave us the best statistical results. Compared to GWLR, GWLR seemed to outperform to GLR in all metrics, as we observe in the summary statistics. For instance, you can see that there's a higher pseudo R-square and lower deviance for GWLR, which indicates a better fitting of the model. And furthermore, there's also a lower AIC and AICC statistic for GWLR, which suggests that GWLR has a better balance of the model fitting and complexity overall. Overall, from the coefficient estimates, we do observe that there are spatial variations among all the different variables, and notably many factors show both positive and negative correlation in different parts of the study area, which further demonstrate the spatial variation of their contribution to landslide susceptibility. So for instance, you can see that slope angle has small variations in coefficient estimates, mostly indicating a positive correlation with landslide risk. Coefficient estimates for profile and plane curvature, on the other hand, show larger ranges with negative values, suggesting that perhaps upward convexness and sideward concaveness increases landslide risk. And interestingly, land use vegetation is positively correlated with landslide risk in most of the study area, which contradicted with our initial hypothesis that more urban areas lead to more susceptible areas to landslides. In addition, since plutonic and metamorphic lithology exhibit both negative and positive coefficient estimates, relating the varying coefficient estimates to underlying geological structures could perhaps provide further insight into the changing relationships between predictors and landslide susceptibility, which we might want to explore in the future. And a positive correlation between average precipitation and landslide susceptibility was also observed, but there are also extreme cases we observed where the increases in precipitation either significantly increased or decreased landslide risk. But nonetheless, the overall results do highlight the importance of considering spatial variations and the need for alternative empirical data to quantify land use in further studies. So here is the final landslide susceptibility map we generated using the GWR model after considering our selected variables. And having such a landslide susceptibility map helps to communicate with non-technical specialists about areas with higher susceptibility, and also enable them to implement and facilitate the necessary mitigation measures they need to implement so that they can enable the local community to better prepare for landslides. Now I'll pass the time back to Kai to share about the rest.
All right. Thanks, Victoria. So as for the conclusion remarks, we explore the advantages of using local or spatial statistical models in geoenvironmental analysis like landslide susceptibility. These models overcome the limitations of mathematical abstractions that are common in statistical model by capturing complex local structure, and this is then by dividing a global model into local sub-model and using primacy over neighboring data. As well as, moreover, in specific to the GWL model that we explore in our study, the use of bandwidth and the Gardner functions allows spatial dependence which as suggested by Tobler's law for geography to be effectively incorporated in the model formulations. And as a result, by addressing spatial non-stationarity present in global models, our study has demonstrated that local statistical model can produce more accurate and region-specific outcomes, and this can lead to better predictions and the mitigations of landslide risks in different areas. However, definitely this is not a generalizable finding. Rather, it serves as a starting point for further explorations of how we can incorporate such spatial characteristics and local spatial structures into the formulation and the training of other global models, probably maybe machine learning models, since our study focused on statistical model for now. Can be the future work and the future research direction that can set forward based on the research finding from our study. And with that, we would like to wrap this presentation. Thank you so much. And we would love to hear your opinion, comments, or questions. Thank you.
Let's see if there is a question. I don't know if anybody want to ask a question.
May I ask?
Yeah.
So I have just one question. Which parameter is the most important for your map? Which parameter is the most important? Or maybe several parameters are very important?
Okay, so wait, let me share the screen again. Sorry. This one, right? Okay. So, in terms of parameter, right, the nature of the modeling technique that we use here itself is that. Sorry, not here. Give me a moment. The nature of our model is that because we are focusing on the spatial variations. So, in a global statistical model, you get one coefficient for one factors, and then we can look at the coefficients and see, okay, which factor has the highest correlation with the landslide rates. But however, in our local model statistic, we don't have one, but we have local coefficient estimate for every single data observation. So if you see in some spaces, there might be higher correlation with landslide susceptibility, and in some area, the same set of variable can have lower rates of landslide susceptibility. This is exactly what we show in terms of how the contribution of factors can in fact varies across the space. So if we have to ask your question, we definitely cannot draw a definite answer on which variable has the highest contribution to landslide. However, if we have a specific location, a specific data point, we can look at the local statistic for that specific point, and we can see what set of variables contribute to landslide susceptibility the most. But in overall, since we're looking at the local structure, we cannot give a generalized or an average answer for that. Hope this clarify.
Thank you.
All right. Is there any more questions?
Okay. Thank you so much.
Thank you so much.
Okay. Next one. Sarah, are you there? The trajectories in Rutherford expression according to Lagrangian dynamics. Okay. Najda? No. So I think Maxim, you will be the next. If you are present, we can go on.
Now?
No.
Or we wait until 16:30. No?
Okay, so
should we wait or I can present now?
No, you can present. We will see if they join later. We can do it after you.
Okay.
You can go on. Okay, thank you. You just have to share your screen, please.
Let me just share my screen. Do you see my screen?
Yeah, perfect.
So, okay, I can start?
Yes, please.
So, good day, ladies and gentlemen. My name is Maxim Protasov, and I will present asymptotic full waveform inversion in the image domain. Here is the contents of my presentation, and I will present briefly the motivations. Then I start with the standard full waveform inversion in the data domain. And next, I will come to asymptotic full waveform inversion in the image domain. Then I will show numerical examples, and I will finalize with the conclusions. So the motivation is the following, and it contains two parts. The first one is connected with the fact that the standard acquisition system used in 3D seismic survey includes tens of thousands to hundreds of thousands of sources corresponding to different right-hand sides in the seismic modeling problem. And at the same time, each separate task calculation of one source's field requires a supercomputer when using finite difference modeling. As a result, the necessary computational resources for modeling seismic data for a typical acquisition system can be estimated at 10 to the power of 8 core hours. Therefore, developing and acceleration of algorithms for numerical modeling of seismic wave fields for FWI is an urgent task. And one of the possible alternatives is usage of asymptotic methods, which are much faster than finite difference.
See the first slide of your presentation.
Sorry?
We still see the first slide of your presentation.
Should I restart presentation?
Maybe.
Okay. And now which slide do you see?
Yeah. Thank you. Yeah.
Okay, let me do like this. So the second part is connected with the fact that the success of the full waveform inversion is very sensitive to the quality of the seismic data, and it is almost impossible to satisfy this kind of requirements of this approach, for example, in areas with complex near-surface conditions. And it comes from the standard implementation of FWI in the data domain, while the potential solution can be the inversion of seismic wave fields in the image domain, where the signal-to-noise ratio is much higher. So that is why we do it in the image domain. So now let me come to the standard full waveform inversion in the data domain. So we consider the Helmholtz equations that describe waves in acoustic medium with constant density. And using Helmholtz equation, we introduce the forward modeling operator. And the general FWI formulation in data domain is to find the minimum point of the misfit functional characterizing the mean square deviation of the recorded data from those calculated for the current velocity model. And the gradient of FWI problem in the data domain is calculated as follows. The gradient calculation in this case is reduced to the calculations of Green's functions for all positions of sources and receivers. And the standard way is to use finite difference solution of wave equation for Green's function calculations. This way we call standard FWI, and it is computationally expensive. And therefore, acceleration of calculation of this part, Green's functions computation, is of a big interest. And therefore, we come to asymptotic full waveform immersion in the image domain. And full waveform immersion in the image domain minimizes the functional built in the image domain. And in this case, the asymptotic beam migration operator is used, which transfers the data to the image domain where the minimization takes place. So, and the gradient of asymptotic FWI in the image domain is calculated as follows. And it turns out that the gradient in the image domain is the sum of two components. First component is the analog of the gradient in the data domain, and the second part associated with the dependence of the migration operator on the model. Therefore, on the one hand, the FWI in the image domain should be more informative. On the other hand, it is more stable since images have a better signal-to-noise ratio than seismic data. And it should be computationally cheaper than standard FWI because asymptotic modeling is much cheaper than finite difference modeling. And next, in the data domain, the data domain analog of the asymptotic FWI gradient is omitted, and the expression for the derivative of the image misfit function is transformed, and the gradient gets the following asymptotic approximation. And the God gradient is similar, actually, to the gradient of the tomography operator, because there are the trial derivatives with respect to model parameters. And therefore, this part of the gradient is called tomographic part of the asymptotic full waveform inversion in the image domain. And indeed, when considering the linear step of the full waveform inversion, one can come to the following asymptotic representation of the image misfit function containing only the tomographic part. At the same time, the linear step of the reflection tomography problem provides the following expression. And here are delta t is the travel time residual between observed reflective travel times and the computed in the current model. One can observe that the similarity of this, there is similarity of this expression. For the tomography case, it has a tomographic operator in right-hand side and travel time residual in left-hand side. For the asymptotic FWI case, the expression consists of weighted tomographic operator in the right-hand side and image misfit in the left-hand side. This means the expression for image domain FWI problem is the dynamic analog of the expression for the kinematic problem. So, and now let me come to the numerical examples. The numerical examples were provided for the well-known model that is the freely available Marmouzy P-wave velocity model. And the acoustic modeling in this case is using the finite difference scheme for the wave equation, and therefore we provide seismic data. The data set simulates the 2D line survey, seismic survey, in which observation consists of 320 sources, and the distance between sources equals to 50 meters. And each source provides a signal recorded by 81 receivers. The distance between the receivers equals to 25 meters, and therefore the maximum source receiver offset equals to 4 kilometers. The modeling utilizes the Ricker's impulse, and the dominant frequency is 15 hertz. And on this figure provides the example of the seismogram with the source position at x equal to 500 meters. So, and for the investigation of the possibilities of proposed asymptotic FWI in the image domain, the inversion process uses different initial models. The investigation provides three essentially different scenarios. In the first one, the initial model comes from a reasonable 1D depth strength of the model, and finally it represents a laterally homogeneous model. This model has a big difference with the true one, and in that model the beam migration result shows the highly defocused events and essentially incorrect positions of the reflection interfaces, especially below the depth of 2,500 meters. The first experiment provides a comparison of the results of the common image point tomography application and proposed asymptotic FWI in the image domain for the described inversion scenario. Here are shown the results of the linear step application of common image point tomography and the results of the linear step application of asymptotic FWI in the image domain for the laterally homogeneous initial model. The tomography provides the inverted model that becomes closer to the true model in comparison to the initial one. The inverted model is similar to the smoothed Marmouzy model, actually. And the results of the proposed asymptotic FWI in the image domain are different completely from the results of common image point tomography. And we can see that proposed FWI result does not give the satisfactory inverted model result. Then we come to the second scenario, where the initial model contains the lateral variations that comes from the true model. The initial model is a strong smoothing of the true Marmouzy model, and here the initial model has a smaller difference with the true Marmouzy model in comparison with the initial model from the first scenario. However, the difference is still essential. And the beam migration results in this case provide better focused events and more correct position of the reflectors, while they are still mispositioned significantly. Here are and now here are shown the results of the linear step application of common image point tomography and the results of the linear step application of asymptotic FWI in the image, but for the second scenario now. Again, one can see that the tomography provides the inverted model that becomes closer to the true model in comparison with the initial one. And the inverted model is also similar to the smoothed Marmouzy model. However, the proposed asymptotic FWI doesn't give the satisfactory inverted model results still. The explanation of such results for both scenarios consequence from the investigation for the time domain FWI in the data domain, where the so-called cycle skipping problem arises. Because traces in the image domain are analog to the traces in the time domain, therefore image domain inherits this cycle skipping problem. For the last scenario, the initial model is a slight smoothing of the true Marmouzy model. Here, the initial model has no such big difference with the true Marmouzy model, but it does not contain the high frequency component of the true model, and it provides a sensible difference of the kinematic properties in comparison with the true model. The beam migration result in this model provides an image with reflectors positioned that are in reflectors positions that are close to the true ones. However, there is a slight difference in most of the model, and it becomes essential in the central, most complex part of the model. So, and finally, for the last scenario, here are shown of the linear step application of tomography and the results of the linear step application of asymptotic FWI in the image domain. So in this case, the tomography doesn't provide any reasonable update of fine structure, but still it gives the residual smooth part of the model. However, the results of the proposed asymptotic FWI in the image domain shows model improvement. Here, the initial model is close to the true model, closer to the true model, and therefore there is no influence of so-called cycle skipping problem. The reconstructed model is closer to the true model in comparison to the initial model that is used for the inversion. And here the model update contains a more detailed, higher frequency components compared with the model update got by common image point. Also here I have to say a few words about computational speed up of asymptotic FWI in comparison with the standard FWI. The computational time for all experiments that I have shown is almost the same, and the computational time for common image point tomography experiments are almost similar to the computational time of asymptotic FWI experiment. It means that proposed asymptotic FWI in the image domain provides a computational speed up comparing to the standard FWI, because it is well-known fact that common image point tomography faster than standard FWI approach. And for example, computational cost of common image point tomography applied to real seismic data from the area around 1,000 square kilometer is estimated by days using rather powerful computer cluster, while computational cost of standard FWI based on finite difference model may be estimated by months on the same data and using the same computational cluster. And finally, I come to conclusions. This work provides the new asymptotic full waveform inversion method in the image domain and its investigation. The classical FWI solution uses a computationally expensive finite difference solution of the wave equation. The asymptotic approach uses ray tracing to solve wave equation and Gaussian beam migration, which makes it possible to speed up the gradient construction procedure in comparison with the standard FWI. The comparison of asymptotic FWI and common image tomography shows that the speed up of calculation of both methods is similar, while CIP tomography is much faster than the standard FWI approach. Also, the comparison shows that proposed asymptotic FWI and common image point tomography provides reconstruction of different model parts. A series of numerical experiments for other complex Marmouzy model shows that common image point tomography is effective in reconstructing low frequency model, while asymptotic FWI provides recovery of the details of complex velocity structure. And finally, I have to say that the work is supported by a RSF grant, and thank you for the attention. And if you have any questions, I will try to answer them.
Thank you so much. Let's see if there is any question. No question.
There's some message in the chat, is it? There is also messages in the chat.
Yeah.
Question.
Okay, there is no question. Thank you so much for your presentation. And let's see if the next one lecturer is present here. Frequency-dependent ray of QP waves in 3D weeks, titled Transversely Isotropic. Dimitri and Maxim, any of you are present? Yeah.
Hello, everybody. Do you hear me?
Hello. Yeah. Could you please share your screen?
Yes, I'm trying.
Okay, thank you.
Что я показываю?
Okay, perfect. And you have 15 minutes.
Do you see my screen?
Yes, perfect. Yeah. You can start.
Here is outline of my presentation. First of all, I describe the motivation of our work. After that, I say a couple of words about approximate expression for phase and group velocities of quasi-primary wave in weak TTI medium. After that, I describe algorithm for calculation of frequency-dependent rays in TTI medium. After that, I show some numerical example and made conclusion. So, many technical applications require calculating travel time and travel path between known locations of source and receiver from some probing system. Seismic exploration, such problem known as ray tracing, and it plays a significant role. Modern problems arising in seismic exploration are often dimensional. Spatial size of computational domain may be huge. Data processing techniques such as depth migration or seismic tomography should be computationally efficient. It means that ray tracing subroutines, which are part of any seismic data processing packages, must be effective. Ray-based methods are usually used in high-frequency approximation of seismic signals propagations. Classical ray method doesn't take into account the effect caused by band-limited nature of real seismic signals. High-frequency approximation often leads to the non-physical behavior of rays and corresponding tail times. Here is some example of non-physical behavior of standard or high-frequency rays in complex model. Ray distribution is very regular. The limited spectrum signals propagate in some volume surrounding the rays, so-called Fresnel volume. Dominant frequency of the signal determines the width of this volume. A number of methods are developed to go beyond the standard ray method based on high-frequency approximation. The main idea behind these approaches is to consider the impact of the Fresnel zone on travel times and travel paths. The principal disadvantages of the already existing method approaches is the complexity of the calculation, especially in three-dimensional case. So, previously, we proposed new method for frequency-dependent ray calculation in 3D acoustic medium. This procedure involves moving a locally flat fragment of wavefront, those orientations depend on the velocity distribution inside a certain frequency-dependent aperture. The parameters of the medium affect the ray within a certain volume around it. We refer to this rays as, we call it as a fat rays because of this reason. The suggested approach has proven to be quite robust and easy to implement. Numerical experiments demonstrate that fat rays are more stable in complex situations than standard rays and may provide reliable travel times and trajectories when the standard ray method fails. In this presentation, we discussed extension of this method for anisotropy because industry widely acknowledges the need to consider anisotropy in data processing practices. We describe an algorithm to compute frequency-dependent rays of UP waves in three-dimensional TTI medium with arbitrarily oriented symmetry axis. So in seismic exploration, the propagation of UP wave is mostly interesting. The following parameterization of the anisotropic medium is used in practice if only QP waves are taken into account. So we defined phase velocity of QP wave along the symmetry axis. Also, we define orientation of the symmetry axis in each point. And also we need two anisotropy parameters, epsilon and delta, which is so-called Thompson parameters. Thompson parameters are expressed through the density normalized stiffness tensor coefficients. I do not show it here. This slide presents the approximate expression for phase and group velocities of QPFs, which we use to calculate frequency-dependent rays. In most realistic cases, the assumption of weak anisotropy is valid. By making this assumption, the expression of phase and group velocity can be greatly simplified, which significantly increases the computational efficiency of ray tracing in isotropic medium. So here we can see expression for phase velocity. We can calculate it using normal orientation and parameters of the medium, Thompson parameters and phase velocity and symmetry axis orientation. After that, we can calculate group velocity. Group velocity defines the direction of energy propagation. So now I describe the algorithm itself. As an input, two angles are given which define initial orientation of the wavefront normal. First angle is azimuthal angle. Second one is dip angle, namely an angle between initial normal and vertical or z coordinate axis. Let xp is a current point on the ray. we will call it central point. Also, unit vector n is given at this point that defines orientation of the wavefront, is normal to the front. To move along the array, we need to define new position of the array, and new normal orientation. So the next step is phase smoothing the central point. We construct a plane, thus draw the point xp, which is orthogonal to the normal n. In this plane, we cut a rectangular area. It represents a fragment of locally flat fragment of wavefront. The size of this rectangular is a function of local wavelength in the central point. A regular grid is defined in this rectangular. In this figure, blue asterisks represent those grid points. In each grid point, the phase velocity value along the normal direction are calculated using expression I presented above. At the central point, the weighted sum of all phase velocity is used to calculate the value of the smooth phase velocity along the flat wavefront element. Here we use Gaussian 2D Gaussian function as smoothing function. So now we have calculated the wavelength smooth phase velocity at the central point. Also, we have symmetry axis orientation of this point and model parameters. Using the smooth phase velocity, the central point, the corresponding group velocity vector are calculated using the approximate expression shown above. During the time interval t, the central point moves to the new point along the group velocity vector. It gives us a position of the next point on the array. So now we need to determine new local wavefront orientation, new normal. So the next step is we consider a circle lying in the same plane orthogonal to the normal, the current normal n. Radius of the circle is also a function of the local wavelength. Further, those points are referred as control points. We choose a number of control points lying on the circle with constant angular increment. So for each control point located on the circle, a group velocity is calculated. For the same time interval dt, the control points travel different distance because group velocity values may be different. It's highly probable that that new control point location will not be in the same plane. So control point in updated position might not be in the same plane. We define numerically a plane which is closest to all points in the least square sense. So classical linear regression problem is solved. Numerical solution of this problem allows us to calculate a new normal vector to the front end. And final step is we attach this vector, this normal to the new central point position and repeat the process. In this manner, we approximate the propagation of locally flat element of wavefront. The physical parameters of the model in the particular vicinity of the array affect its orientation in each moment of time. So we verified the proposed approach by comparing the frequency-dependent rays with the standard ray in the smooth model. We use the smooth model to prevent problems with standard rays, as they exhibit unpredictable behavior when there are sharp inhomogeneities within the model. As the theory predicts, if the ray frequency parameter or width of the smoothing aperture decreased, the fat rays should tend to be closer to the standard rays. Numerical validation of the proposed scheme is based on this fact. So the numerical experiment is based on the realistic model obtained during real seismic data processing. The data set was acquired in some oil production area in eastern Siberia. Isotropic reflection real-time tomography was used to recover model parameters. Phase velocity of QP waves along the vertical axis of symmetry vary between 1,400 up to 3,050 meter per second. Dimensionless Thomson parameters epsilon and delta lie within the range between 0 and 0.2 respectively. Symmetry axis is vertical in each point of the model. Like here, we exploit the high frequency asymptotic properties of flat rays. In this case, we must achieve the best match between flat rays and standard rays. Standard rays are calculated using standalone isotropic ray tracing code borrowed from well-known package Madagascar, produced in Texas University. Figure on the left shows a 3D view of 50 rays calculated for a fixed azimuth. One can see that fat rays correspond closely with standard rays. Maximum deviation of ray trajectories for more than 5 kilometers travel path do not exceed a few meters. We have compared so-called first arrival travel times tables of QP wave calculated using fat and standard rays. The travel time residuals between standard fat rays do not exceed 3 milliseconds. It is anticipated that fat rays will be utilized in media that are more sophisticated than the model presented here in this slide. Then dealing with complex model with sharp interfaces, classical rays may struggle to calculate adequate ray trajectories and travel times. As demonstrated in our previous publication, previous slide, fat rays with properly selected parameters can handle this task quite effectively. And finally, in this slide, we present 3 components of the frequency domain wave field calculated using ray method. The vertical point force source was used. Solution error provided by fat rays in comparison with exact solution provided by exact finite difference modeling do not exceed few %. So, and finally, my conclusion: fat rays allow simple and efficient approximation of the broadband signal propagation. Comparative analysis of flat and standard rays was performed, and results show the prospect of using 3D anisotropic rays in seismic application. Here is my acknowledgement. That's all. Thank you.
Thank you so much. Let's see if there are some questions. No question. Thank you again. And I don't know if the other lecturers are here with us, or we can close this session. Sara Chunga Palomino, Edward Klein Maza, and Robert. Any of you are here? No. Sure. Najada,
thank
are you there? Najada Firza? No. So thank you so much, and we can close the session today. Have a nice day and goodbye.
Thank you. Goodbye.
Thank you.